Hi, and welcome to C.1 Simple Harmonic Motion, one of my favourite topics. And why is it my favourite topic? Yeah, I'm going to say it's my favourite topic. It's my favourite topic because there's some good maths in it, there's some great graphs in it, and actually the exam questions tend to be pretty easy once you know what you're doing. So I'm sure it will become one of your favourite topics as well. You'll notice that this topic is split into two sections. Section 1 is standard and higher level, and then there's a small section at the end which is higher level only. And really the only difference with the higher level stuff is that you have to perform calculations with energy and SHM, whereas in the standard level you just need to describe the energy changes. What is simple harmonic motion and how can I recognise it? So let's look at my three examples. Our first example is a pendulum. Let's have a watch of this pendulum. Try not to fall asleep. This pendulum is oscillating backwards and forwards. And it's oscillating around an equilibrium, which would be when the pendulum is straight down, pointing straight down. There's a restoring force here. That restoring force, pulling it back towards equilibrium every time, is the force of gravity. Our next example of simple harmonic motion is this wave. You can see we have a transverse wave, and the energy of the wave is being propagated to the right of the screen. But if you concentrate on one particle within that wave, you can see that it's oscillating up and down, up, down, up, down. Its equilibrium point is in the middle of this wave. Our third example of an oscillating system, or a system exhibiting simple harmonic motion, is this mass that's oscillating up, down, up, down, up, down, up on a spring. It's oscillating around an equilibrium point, and the restoring force is the force due to the spring when it pulls it up, and gravity when it pulls it down. We have looked at some examples of simple harmonic motion. Let's take one particular system, and what you can see here is we have a cart, and on either side of the cart we have two springs, and these springs are fixed in position on either side. When this cart is in equilibrium and it's not moving, the force on the cart is 0, the acceleration of the cart is 0, and its displacement is 0. Let's move the cart to the left. Pull it over to the left. You'll see that the springs have changed form. The spring on the left-hand side has become compressed, and it's desperate to push the cart towards the equilibrium. And the spring on the right has become extended, and it's desperate to pull the cart towards equilibrium. So if we look at the force on the cart at this point, it's maximum when it's at its amplitude, its maximum displacement, and it's pulling it back towards equilibrium. It's restoring it back to where it was. We call it the restoring force. The force is pointed in the direction of the right. So we've said right is positive because you can see here that's a positive amplitude and that's a minus amplitude. So it's in the positive direction being pulled back towards equilibrium. If the force is pulling the cart towards the right, that means it's accelerating towards the right. If the force is maximum, it means it's a maximum acceleration towards the right or in a positive direction. If we take a look at the displacement of the cart at this point, we can see that the displacement of the cart is to the negative side of equilibrium, and it is the maximum displacement in the negative side. Let's now look at the cart on the right-hand side. You can see that the two springs have changed form yet again. This one is compressed and pushing the cart that way. This one is extended and pulling the cart this way. Again, it's restoring force back towards the equilibrium. It's a maximum force felt at this stage, and it's in a negative direction. If the force is in that direction, then the acceleration of the cart must be in that direction as well. So we have a maximum acceleration towards the equilibrium. By contrast, what we have with displacement is it's a positive displacement and it's still maximum, and that is in the opposite direction to what the acceleration was. Now, if we relate this to what the examiner feedback has been for questions relating to simple harmonic motion, the actual examiner feedback says that candidates had difficulty with explaining the conditions required for simple harmonic motion. So let's go back to this idea of the cart. If we look at the acceleration of the cart, we know that the acceleration of the cart is maximum here, and the acceleration of the cart is maximum here. We also know that the displacement of the cart is maximum here, and the displacement of the cart is maximum here. They both increase by the same factor, and they both decrease by the same factor. This means that the first condition for simple harmonic motion is that acceleration and displacement are proportional, only in magnitude, because the displacement of the cart here is positive, but the acceleration of the cart is negative. And if we look at the cart at this position here, the displacement is negative, but the acceleration is positive in that direction. So the second condition for simple harmonic motion is that they act in opposite directions. So we know that an object that is oscillating is undergoing simple harmonic motion when the acceleration and displacement are proportional and they act in opposite directions. Why am I hammering this home so much? Okay, well, let's have a look at a past exam question. You can see here we have a mass on a spring. We're very familiar with that now. I'm going to read the question out for you. An object of mass m is placed on a frictionless surface and attached to a light horizontal spring. The other end of the spring is fixed. The equilibrium position is at B. The direction B to C is taken to be positive. The object is released from position A and executes simple harmonic motion between positions A and C. Define simple harmonic motion. Simple harmonic motion is defined as an object who undergoes the conditions for simple harmonic when oscillating. These conditions are the acceleration and displacement are proportional, they act in opposite directions. 2 marks. Let's have a look at another question. The acceleration A of a wood is related to x by the following equation. So we have acceleration equals minus 14 over L. L we assuming is the length of wood. X, and X is displacement. Explain why this equation shows that wood is executing simple harmonic motion. Okay, well, if we assume that the length is constant, then this whole value here is constant. Okay, so we can say that A is proportional to minus X. So, how do we know that this equation is executing simple harmonic motion? Well, A is proportional to X, acceleration and displacement are proportional, and they are acting in opposite directions. The minus tells us that when this is minus, that's positive, and when this is minus, that's positive. So the minus tells us that they are acting in opposite directions. So these two sentences are key for when explaining when an object is undergoing simple harmonic motion. The theme of waves has quite a lot of definitions in it, and in the past, up to 9 to 11% of the papers have been dedicated to general knowledge in terms of learning definitions, learning facts, and so on. So it's worth just taking time to make sure you understand the definitions of time period, frequency, angular frequency, amplitude, and displacement in terms of a particle of SHM. The time period for an object undergoing simple harmonic motion is basically the time taken for one complete oscillation. And you can see this pendulum here is undergoing simple harmonic motion. The start point is the small yellow dot. And the time period would be the time taken to leave the start point now and return to the start point. And you would simply use a stopwatch to determine what that is. It's measured in seconds and is given the symbol capital T. Frequency, when we're looking at simple harmonic motion, is defined as the number of oscillations per unit time. Per unit time means per second. So how many oscillations are there per second? And this is going pretty slowly. And I think if we were to try and measure 1 second and then determine how many oscillations there are per second, I don't think we'd get a very accurate answer. Then it's quite often a good idea to measure the frequency over, say, 20 seconds and note how many complete oscillations there are then. So let's do that together. When it next hits the start point, I'll set a timer for 20 seconds and we'll count the number of oscillations together. Go. Okay, that's 1 oscillation, 2 oscillations, 3 oscillations, 4 oscillations, and we're coming up to 20 seconds now, and that's 20 seconds done, and that's 5 oscillations. So that was 5 oscillations in 20 seconds. That means that 1 oscillation takes 4 seconds, and the number of oscillations per second is a quarter. So the frequency of this is 0.25 hertz. Another way, and we kind of did it in the example there, another way to find frequency is to take the reciprocal of the time period, or 1 divided by time period. So if we know the time period is 4, then the frequency is 1 divided by 4, which is 0.25 hertz. Angular frequency, so it's a rate of change of angular displacement. And the units for this is radius per second. But I'd like to discuss 2 notes. Note number 1 is that angular frequency is equal to 2 pi over t. And do you remember that frequency is equal to 1 over t? So there's a really nice relationship there that helps you remember what the formula for angular frequency is. And if you want to take a frequency in hertz and convert it to angular frequency, you simply multiply it by 2 pi. Displacement for a particle undergoing SHM is the distance a particle moves in a particular direction from its mean equilibrium position. If you look at the animation here, the equilibrium position is shown. That would be x equals 0. And at any time, you can determine what the displacement from that x equals 0 equilibrium position is just by measuring. You could use a ruler. All right, so the equilibrium is where x equals 0, and x is the distance from that equilibrium position at any time. Of course, there is a maximum distance from the equilibrium position, and that maximum distance is called the amplitude. I would usually give it the symbol A, but in a data booklet, it's been given the symbol x0. And again, of course, that is in meters. Most of the exam questions in SHM have a graph involved, and I want to go through all the graphs you might see when you're looking at a simple harmonic motion question in your exams. Please take time to go through this in detail with me and obviously practice it in the knowledge questions below. Let's have a look at what I call the special relationship. We've talked at length about what the conditions for simple harmonic motion are. And I can say it again for you if you like. Acceleration and displacement are proportional, they act in opposite directions. That means if you were to plot a graph of acceleration against displacement for an object in simple harmonic motion, then we should be able to come up with a pretty simple graph. Let's look at number 1. Acceleration and displacement are proportional. Well, we're very comfortable with this idea of proportionality, and we would draw a graph like that. However, this is not quite right, because if we take condition 2 into account, we see that they act in opposite directions. So we want them both to increase by the same factor, but we want to represent the fact that they go in opposite directions. So we can plot the graph looking like this. So if you have an object that's executing simple harmonic motion, this graph would always be relevant for that object. So if you see this graph, you know that the object is undergoing simple harmonic motion. I'd like to go back to this card, because that's not the only graph that you have to be comfortable with when you're looking at SHM. You can see we've got 3 positions here. A, where the cart is in equilibrium. B, where the cart is in minus displacement. And C, where the cart is at positive displacement. And what we're going to do now is we're going to plot the graph of how displacement varies with time. So let's go over to my desk cam. Here we go. Here is the displacement time graph that I had shown in my previous slide. And if you remember correctly, we'd started the cart at a displacement of 0 and it was in equilibrium. So we can plot a point on our graph there. A short time later, we had moved it negatively towards its maximum amplitude, and we found that it went to its maximum amplitude. So then its restoring force would have forced it back towards equilibrium. So we have a zero displacement again. And as part of that oscillation, it would then naturally flow towards its maximum displacement in the opposite direction on the right, here. And again, the restoring force will pull it back to equilibrium. And as part of that oscillation, it would then naturally go round towards its negative amplitude in the opposite direction and back to equilibrium again, and so on. We know that it's a very smooth operation. We saw from our examples at the very beginning that this oscillation happened smoothly. So we do not want jagged lines, zigzags, joining these dots up. We want to do a smooth curve through the points. Could be smoother. Down through the points and back up again. And so we have a graph of displacement against time for an object in simple harmonic motion. If we look back to our studies in topic 2, we have seen displacement time graphs, and we know that the gradient of a displacement time graph is equal to the velocity. So let's just have a look at these points here. Where's the maximum gradient of this graph? Well, actually, there's 4 maximum gradients. There's one there, one there, one there, and one there. That's where the slope is at its maximum points. So here, if the gradient is maximum here, that must mean it must have maximum velocity there. So max velocity, max velocity, maximum velocity, and maximum velocity. What's different about each of these slopes? Well, that's a negative slope. Negative. So it must have a negative maximum velocity at that point. This is a positive slope. So that's a positive maximum velocity at this point. This is a negative slope. So it's a negative maximum velocity at this point. And this is a positive slope. So it's a positive maximum velocity at this point. Let's look at other points in the graph. Well, here, at this point here, the gradient is actually 0. What does that mean? Well, that means that velocity is 0 as well. So there are other points in the graph where we've got a 0 velocity. We've got this point here. We've got this point here. And we notice that the slopiness or the gradient changes continually between those points. So let's memorize this graph or put it to one side for a moment. Let's go to a velocity time graph. And we started off, I'll go back to our displacement time graph. We started off with at 0, time equals 0, we had a negative maximum velocity. So we go to our velocity time graph and we put a point here at 0, negative maximum velocity. Go back to our displacement time graph. After 2 boxes, but there's no real time shown here, no scale shown here, we can say it's seconds. After 2 seconds, we have a 0 velocity because the gradient is 0. So after 2 seconds, we have a 0 velocity.
Again, after 2 seconds, we have a maximum positive velocity. So go to velocity time graph, 2 seconds, maximum positive velocity. Come back to the displacement time graph. After 2 seconds, the velocity is 0. So back to velocity time graph, make it 0. We then have negative maximum velocity, negative maximum velocity, and so on.
So if we make this graph nice and smooth, plot the points, and join them up. You can see we have a nice oscillating graph. Now let's go back to this displacement time graph. This starts at 0 and it forms a nice curve. We know that this is a sine curve. if we look at the velocity, you can see it starts with an amplitude. This is a cosine curve. We also know from topic 2 that the gradient of a velocity time graph is equal to acceleration. So at this point here, we have maximum gradient, which means maximum acceleration, and it is positive. Here we have a maximum gradient, so acceleration, is maximum, and it is a negative gradient, so it's negative. And here we have acceleration, maximum acceleration, and it's positive. At these points here, that should sort of be curving round. That's got a gradient of 0, which means acceleration is 0. Here, we have a gradient of 0, so acceleration is 0. And here we have a gradient of 0, so acceleration is 0, and so on. So if we then plot an acceleration time graph, we can use this detail to plot an acceleration time graph. So we're starting, this is our velocity time graph. We see that the gradient is 0 at this stage here, so our acceleration is 0 on the t equals 0 axis. Then we go to a positive maximum gradient, which means a positive maximum acceleration up here.
Then we go to a 0 gradient, which means a 0 acceleration, which is down here, and I think we can sort of that's over there.
Let's join the dots. So our acceleration time graph for this oscillation looks like that. It's also a sine wave. Let's go back to the displacement one. Displacement was a sine wave. Acceleration is a sine wave. But they start in opposite directions. So acceleration and displacement are in opposite directions, which is one of the conditions of simple harmonic motion. And these displacement time graphs and acceleration time graphs prove that to be the case. Given that we now have a very detailed understanding of the graphical nature of SHM, I want to push that on a little bit and start exploring the maths behind it, because the maths behind it will allow us to derive the defining equation for SHM. You don't need to know this derivation. However, it is fundamental to where the equation comes from, and it's fundamental to your understanding of answering anything to do with SHM in exam questions. We looked at the graphs of simple harmonic motion for displacement versus time, velocity versus time, and acceleration versus time, and we noted the similarity and differences between the three. We need to drill into a lot more detail on this and really put our mathematical skills to the test. Let's start with a displacement time graph for an object exhibiting simple harmonic motion. We have this graph now that we can easily recognise the shape of, but let's put our maths to the test. The equation of this line is either a sine or a cosine function, and we can see that it starts with an amplitude of x0, so it must be a cosine function. So we can see the equation of this line is x equals cos omega t, and that's to do with the time. And our amplitude goes in the front of it. Omega is the angular velocity of the object, and this is thought to be a constant at this stage. We know that if we differentiate displacement with respect to time, we can obtain a formula for velocity. So let's do that. I've differentiated displacement with respect to time, and we've come up with this formula here. Let's have a look and translate that to the graph. So velocity of the object is equal to minus x0 omega sine omega t. So that means that our maximums here must be, let's put it around a nicer way, x0 and omega x0. And you can see actually visually that graph doesn't have as large an amplitude as that graph. Okay, but again, this omega is a constant throughout. Omega is a measure roughly of how close together these waves are, and that stays the same for the displacement and the velocity time graph. One wave takes 1, 2, 3, 4 periods of time, and one wave here takes 1, 2, 3, 4 periods of time. Now that we have this formula for velocity, v equals minus omega x naught sine omega t, we know that the acceleration of an object is equal to the velocity of the object differentiated with respect to time. So let's do that. Let's do minus omega squared x naught cos omega t. And if we go to the graph, we'll now say that these parts here are omega squared x naught minus omega squared x naught. So again, you can visually see that the amplitude of these oscillations have increased, but the passage of time, 1, 2, 3, 4, remains the same. So omega remains the same. Let's look at these two formula for displacement. We started off with displacement was x naught cos omega t, and acceleration is equal to minus omega squared x naught cos omega t. Can you see that there are two factors here that are the same? X is equal to x naught cos omega t. So instead of x naught cos omega t here, we could put x. So we can see this equation is A equals minus omega squared x. And I'm hoping that you recognise this equation, because this is the defining equation of SHM. Here are the key points that you need to recognise about simple harmonic motion. That the defining equation of SHM is A equals minus omega squared x, where omega is equal to 2 pi over t. And that is not unusual. We had a look at this special relationship for SHM. And we said that the conditions for simple harmonic motion are that acceleration and displacement are proportional and that they act in opposite directions. So if we look back at this defining equation for SHM, if this is a constant, then acceleration and displacement are proportional, and the minus sign suggests that they act in opposite directions. Now this means that omega has to be a constant. So if omega is equal to 2 pi over t, then t must be constant throughout, and t stands for time period. So what we do know about simple harmonic motion is that the time period of the motion is independent of amplitude. Therefore, if we change the amplitude of the oscillation at all that will happen is that the object will oscillate faster to maintain the same time period. So the time period doesn't change if you change the amplitude. A consequence of that is, if you change the amplitude and the time period stays the same, then the velocity of the object must increase. And these two concepts are examined quite regularly in the exam papers, usually in the multiple choice questions. Now, if I go to the data booklet for simple harmonic motion, there are so many equations and they look really complicated. But in fact, there are only 4 that you really need to be comfortable with, and the rest can be managed on the day. The first one, omega equals 2 pi over t, you should be comfortable with and should be able to calculate. That should be a basic requirement for you. The second one is the defining equation of SHM, and again, you should be able to use that on basic problem solving. What I have seen in many exam papers is they ask you to find the maximum velocity as it happens. And now the maximum velocity happens at equilibrium. So if we take a look at this equation here, v is equal to plus or minus omega square root of x naught squared minus x. The maximum velocity happens when x is equal to 0 at the equilibrium. In which case, if you're asked to find the maximum velocity, it actually simplifies down quite quickly, and you can use Vmax is equal to plus or minus omega squared x. Similarly, if you're asked to find the maximum acceleration happens at the extremes when the object is changing direction rapidly. And in that case, at the extreme, that is known as the amplitude. So if you're asked to find the maximum acceleration, you should insert the amplitude at this stage here. In section 2, we looked at the definitions of SHM. We looked at time period, frequency, and so on. And really, to calculate the time period for one complete oscillation, you're going to use the equation, which would be time period equals 1 over frequency, or you're going to use the graph, or you're just going to measure it, right? But there are two very special equations that you must be able to use. Those two equations are for calculating the time period of a mass spring system and calculating the time period of a simple pendulum. We're going to look at these equations now. I'm going to give you a little hint of where they come from, and I'm going to show you where these questions tend to go in exam-style questions. Hint, we're going to be looking at another graph here. Okay, the goal here is to find an expression we can use to find the time period of a mass spring system. And by a mass spring system, I mean a spring that's attached to a mass and is allowed to oscillate. When you think of a spring, you will, I hope, think of this, F equals kx. It is, of course, Hooke's law. When you pull a spring down, or when it's displaced downwards, the restoring force acts upwards, and the magnitude of the restoring force is given as kx. K is the spring constant, and x is the displacement, the amount of distance from the equilibrium position. And because the restoring force is always acting towards the equilibrium, instead of using F equals kx, we can use F equals minus kx, because we know that the force is always acting in the opposite direction to the displacement. This restoring force acts towards equilibrium, but also causes the spring to accelerate. And we know that A is equal to F over M. So let's take that, A equals F over M, and instead of F, let's put in minus kx and work through a little bit. Well, what we can find is that A is equal to minus k over m x. That reminds me of something, because A is equal to minus omega squared x, which is a defining equation of simple harmonic motion. And if the spring is undergoing simple harmonic motion, which it is, then that tells us that omega squared is equal to k over m. Oh, there we go. Omega squared is equal to k over m. All we need to do now is start thinking about this. And with a little bit of work, you can come up with an expression for the time period of a mass spring system. And this is your expression here. This is the expression you would use if you needed to find out how long it takes for one complete oscillation of a mass spring system. And you can see it's only dependent on the mass that's attached to it, in kilograms, and the spring constant, which is newtons per metre. That's a relatively simple equation to use. All you have to do is remember to use it. It's in the data booklet. You don't have to memorise the equation. Just remember that that's what you use for a mass spring system. Where it gets interesting is the exams. In the exams, they'll start to look at graphs. And I'm going to explain this graph in a second. Let me just go back to this equation first. T is equal to 2 pi, the square root of m over k. I'm going to square both sides. T squared is equal to 4 pi squared m over k. I'm going to rearrange it slightly. T squared is equal to 4 pi squared over k m. Okay, let's substitute out these. That is x, that is m, that is y. Y equals mx, which is the equation of a straight line through the origin. So if we plot t squared on the y-axis and m on the x-axis, then you should get a nice straight line through the origin, and the gradient is equal to 4 pi squared over k. So in theory, if you had a mass spring system and you changed the mass, make that the independent variable, and then you measured the time period, that's your dependent variable, then once you plotted them, you would be able to find out what the spring constant of the spring is. This graph and this system is something I'd expect you to see in your data analysis questions in your exams. And similarly, I want you just to imprint this on your brain right now, because I'm going to go to the pendulum system, okay? The equation for the time period of a pendulum looks almost exactly the same. And if you want to go and try and derive that, you're very welcome to. You don't need to. But you can see that the equation looks exactly the same. The only thing that's different is in the previous equation for the mass spring system, this was an M and this was a K. What we got instead, well, we've got length and we've got G, which is a gravitational field strength. So if we take this equation and square it, T squared equals 4 pi squared L over G. T squared equals 4 pi squared over G L. Plot that on the x-axis, that's our gradient, and that is y. Y equals mx, so we put t squared on the y-axis, L on the x-axis, and our gradient becomes 4 pi squared over G. So if you have a pendulum, and you change the length of the pendulum, and then measure the time period for all the different lengths, you can plot a graph like this, and you can determine what the gravitational field strength is. Again, it's another key experiment that you would expect, first of all, do in class, but second of all, to answer your data analysis questions on. In Theme A, we looked at energy. We looked at different types of energy and how they can change within one system. We're going to take that knowledge of potential energy and kinetic energy, and we're going to apply it to an object undergoing SHM. This part of the tutorial looks at how the energy changes in SHM. And to do that easiest, we're going to go back to the velocity time graph of an object that's undergoing simple harmonic motion. Now let's think about the velocity and how we can translate that to a type of energy in the system. Well, kinetic energy, EK, is equal to half mv squared. So we can we can have an idea of the kinetic energy of a particle by considering its velocity. So if we look at this case here, the velocity starts at 0 and it increases in a negative direction to a maximum velocity. Now we can't get negative energy because energy is a scalar. So our graph is always going to be above this time axis here. So even though the velocity is traveling in the negative direction, our energy is going to be traveling in the positive direction because it's a scalar. And it's reliant on v squared. So if that's quite small, this value is going to be much, much greater. So we're going to start off our energy like this, okay? And we can see that the velocity of the object goes back down to 0, which means our kinetic energy of the object is going to go back down to 0 at that stage. Again, the velocity is going to go to a maximum, but we don't go onto the other side of the axis because our energy is a scalar. So what we see is that our kinetic energy follows a path like this with time as the object oscillates, and that's our kinetic energy. When the object has its maximum velocity, this is when the object is going through equilibrium. Here and here. At this stage here, it's at the extremes. It's when it's got its maximum amplitude and it's x naught. At this point, it's got its most acceleration and the greatest force applied to it. And it's at this point where it has the greatest potential energy stored in the spring. So when the kinetic energy is very large, where it's going very fast, the potential energy at that point there's no force on it because it's undergoing a point where there's no force acting upon it from the spring. And when the kinetic energy is very small, at the extremes, the potential energy of the system is at its most maximum, and so on. So what we can do now is we can plot a graph of potential energy against time of the spring, or not the spring, of the object in oscillation. Drawing as best as I can. And what you can see is a continual exchange between kinetic energy and potential energy. If we were to add these two amplitudes together at any time, what we'd find is we had kinetic energy plus potential energy added together at any time, roughly speaking, we would find that it doesn't change. And that tells us that the total energy of the system does not change. And that makes sense because we talk about the conservation of energy. Energy cannot be destroyed or created, only transferred into another form. So it makes total sense that the total energy of the system doesn't change. But underneath here, we have a constant exchange of kinetic energy and potential energy. On to the higher level subjects. We are now going to look at something called the phase angle. And I'm going to show you an animation in a moment to describe how the phase angle can be used to describe the state of a particle undergoing simple harmonic motion. The position of a particle undergoing SHM is often given by its phase angle rather than its displacement. And you might not know what that means. So what I'd like you to do is concentrate on the animation below, and in particular the circular one, so the one on the right hand side. And we have a black dot or a black point that's going round in a circle. The starting point is on the x-axis. I'm going to say now is the starting point, okay? As the black point rotates in a circle, the angle it makes with the x-axis at any time can be calculated as omega t. So you can see as it goes round the circle, omega t shows where it projects onto the x-axis. And the red point is a projection on to the y-axis. Can you see that the red point on the right-hand side of the animation is falling in line with the red point on the left-hand side of the animation? What's happening on the left-hand side of the animation? That red point shows the phase angle of the particle at any given point. And the black line of this left-hand side just plots the motion plotted as a function of omega t. So it basically shows a sine curve. I understand that the phase angle might be a little bit tricky to get your head around. What I recommend you do is rewind this video slightly, block out my voice if possible, and just look at this animation. Watch what's happening with the animation and see if you can try and think about how a particle undergoing SHM can relate to a phase angle. In this learning objective, you're asked to calculate properties of an SHM oscillator. And there's really no extra tutorials for this. This is just practicing, right? And you're going to need your data booklet for that. In order for you to calculate the properties of a particle undergoing SHM, you're going to have to use these equations. And let me just talk you through each equation now. So this equation here tells you what the displacement of a particle is at any time. So say you're asked to determine, what's the displacement of a particle at time equals 2 seconds. You would plug in the data for time equals 2 seconds. You'd find out what omega is using 2 pi f or 2 pi over t. You'd work out the phase angle if there's a shift there, and x naught is your amplitude. So you'd plug in your amplitude, and then you'd work out what the displacement is of the particle at any given time. Let me tell you, that's very rarely used. You're very rarely asked to make this calculation here. Similarly, if you wanted to find out what the velocity of a particle at any given time was, then you would use this equation. Again, you would find out what omega is, t, you put in your phase shift, and x naught is your amplitude, and that would be fine. The most common equation that is used here is this. Now let me give you the special occasion where this is most commonly used. The special occasion is where they ask for the Vmax, or the maximum speed of the particle. We know from an oscillation, the oscillation goes up, it hits the extreme, comes right down, passes through the equilibrium, and back up again. The maximum speed is always at the equilibrium, so the Vmax is here. That's when the displacement is equal to 0. So if you're asked to find the maximum velocity, then this here is equal to 0. So we have Vmax equals plus or minus omega square root of x naught squared minus 0, which is plus or minus omega square root of x naught squared, which is equal to plus or minus omega x naught. So your Vmax, if you want to find the maximum speed of any particle within an oscillation, is given by that equation. Finally, in this topic, we're looking at the interchange of kinetic and potential energy during SHM. And we've actually looked at a lot of that earlier when we were looking at the graphs and the energy in the standard level section. So I'm not going to make this section too difficult. In fact, what I'm going to do is do what I did in the previous section. I'm going to go to the data booklet and talk you through some of the equations. And then the best thing for you really is to go to the knowledge questions and the past paper questions in step 2 and make sure you can start to apply these equations. If we go back to our data booklet here, this is the equation you want to use for total energy. And you can see we need to find out what omega is, and you need to know the amplitude. And this is the equation you would use for potential energy. Now, I'm going to ask you, what do you think the equation would be for kinetic energy? Well, total energy is equal to potential energy plus kinetic energy. Therefore, I'm going to go all the way up here. Kinetic energy is equal to total energy minus potential energy, which is a half omega squared x naught squared minus a half omega squared x squared. So we can take the half and omega squared out, and we've got x naught squared minus x squared. And that is your equation for kinetic energy. Now go and practice. Off you go.